Let's move on to technical session 1 of this international conference on coronavirus, past, present, and future. Let me call upon the chairperson, co-chairperson, and rapporteur of this session. Professor Parvez Gol shall be the chairperson of this session. Dr. Pragya Yadav shall be the co-chairperson of, and Dr. Shaheen Farooq shall be the rapporteur for this session. And I request all three of you to please occupy your seats on the dais. And ladies and gentlemen, we have Dr. Gautam Menon as our keynote speaker for this session. He was supposed to join us in person, but because of some unprecedented occupations, he could not make it here. We are lucky to have him online. He's going to deliver his lecture on COVID-19 modeling using computational models that are fairly detailed and new. Before we listen to him, let me give you a brief profile about Dr. Gautam. Dr. Gautam Menon is a professor of physics and biology and director of the Center for Climate Change and Sustainability at Ashoka University. He's a professor with theoretical physics and computational biology groups at the Institute of Mathematical Sciences, Chennai, where he was the founding dean of the computational biology group. He's an adjunct professor in the Department of Biological Sciences at the Tata Institute of Fundamental Research, India. Over to you, Dr. Gautam.
Thank you very much. Let me just project my screen. We can see if that works. Can you confirm that you're able to see my screen?
Yes, sir.
Yes, thank you. And I hope you can hear me as well.
Yes, yes.
So thank you very much. And let me at the beginning apologize for not being there in person. I really did want to come for the conference, but something personal turned up at the very, very last minute, 3 hours before I had to fly. So my apologies for that. And I do hope that this online lecture will make up for my actual physical presence. So I wanted to tell you a little bit about the work that we have been doing on COVID-19 modeling using computational models. And over here, to start by describing simple models for disease spread, and then go on to talk about COVID-19 models and data. Then I will tell you about applications for the first wave, the impact of school reopening, the Omicron wave, school policies, testing policies, etc. Then I will tell you about network models and a particular model that we have been working on called BharatSim. And then I will tell you about what happens looking forward when we discuss the Omicron wave, the requirement for what are called ensemble models, and how to understand what might happen in the future and how to prepare well for the future. So the simplest models for disease look like the picture that you can see on the top left. There are three little boxes that are labeled S, I, and R. And the whole idea behind modeling is to understand how people in a susceptible compartment, an S compartment, move to an infected compartment or the I compartment, and from there move to a recovered compartment. So we imagine that we have a population in which every individual can be classified either as susceptible, infected, or recovered. And then the interaction between these compartments. For example, you need to come into contact with an infected person if you are susceptible in order to become infected yourself. And that determines the transition between these different compartments. The little block that you can see to the right are a set of equations that describe exactly the transitions between the compartments that I showed you in the earlier picture. These models are therefore called compartmental models, and equations that describe compartmental models are essentially the fundamental equations, the fundamental way of describing, certainly historically, the nature of infectious diseases that are transmitted from infectious people to susceptible people. If you solve those equations that you can see on the right-hand side, you get a picture that looks like the one that you see at the bottom, the main panel of that picture. And this is a prediction for how the fraction of infected changes as a function of time. You can see as I change the variables or the parameters that appear in those equations, the Greek letters beta and gamma, I can get a sharp rise in the numbers of infected, or I can get a gradually smoother rise in the numbers of infected. And essentially, all methods of disease control really amount to trying to change the nature of the shape by altering the way in which individuals transfer from one to the other, or by the use of antivirals, by the use of quarantines, etc. All of these are ways in which you can manipulate the parameters that enter the equation that I showed you to get different types of curves, and pushing the curve down, the peak of the curve down, is equivalent to what is called flattening the curve. The first thing that I want to talk about is something called ICCISM model. It's a model that we developed, and its applications to the first wave of COVID-19 in India. So here is a reference to this piece of paper. To this paper, it should appear soon. The idea here is to look at COVID-19, look at the progression of the disease COVID-19 across different categories of patients or people infected. Most people with COVID-19 will be asymptomatic for the disease. From the point of infection, they will be exposed to the disease, then they will enter asymptomatically infected, in which they can infect other people but show no symptoms themselves, and then they move to a recovered compartment. If you're mildly infected, you will go from being exposed to being pre-symptomatic, and then you will enter a symptomatic. So at this point, you have show symptoms, and then you will recover. You can also be severely ill or critically ill, in which case you go from pre-symptomatic to hospitalized, and then to recovered. And if you're critically ill, you can go from the hospitalized compartment into either recovery or into death. And the sizes of these bars here represent, roughly speaking, the time it takes to recover or the time it takes to progress through the different parts of the disease. The model in terms of compartments is a picture that I show you on the right-hand side. It has 9 compartments as opposed to the simple 3 compartments of the S, I, and R model. Susceptible, exposed, pre-symptomatic, asymptomatic, mildly, severely, etc., etc. All of these are different ways of describing this. Each compartment is subdivided into different age bands, so 0 to 10 age band, 10 to 20 age band. The contacts between these compartments, for example, how often does a 20 to 30-year-old contact a 60 to 70-year-old? All of these are implicit in the way the model is defined. It includes mortality, so you can figure out what the consequences in terms of death for using this model for COVID-19. And all of this is embedded in a mathematical framework called a Bayesian framework. And that says you don't have to know the precise values of these quantities, beta, gamma, lambda, all of these things that I've described here, but they can be described by probabilities and probability distributions. Here are the results that we were able to derive for the first wave of COVID-19 in India. We estimate that about 35% of the population was infected in that first wave. We estimate a fairly small infection fatality ratio. This is comparable to the values from influenza, which may describe why the impact of the disease was somewhat small or not very noticeable in the first wave. We calculate the undercounting of cases, and we come to an undercounting of about 20 at the end, although it was larger initially. And we find that deaths have been undercounted by a factor of somewhere between 2 and 5, and a number of about 2.2, 2.3 is the number that we finally settled on. So all of this is more or less consistent with what we now understand about the disease. What's important in models like this is to understand the nature of the data that go into these models, and particularly what are the numbers and rates that are appropriate to India. If you have a complicated model like the pictures that I showed you, first of all, there are what are called branching ratios. For example, someone who's pre-symptomatic can move into the symptomatic or the mildly infected categories here. Someone who's exposed can move either into asymptomatic or the pre-symptomatic. Now, the numbers that we have for the rates and these branchings are all obtained from foreign data. This is currently largely from non-Indian data. We are trying to supplement it with Indian data, but usually Indian data sets are too small, except for one cohort, the CSIR cohort, which is somewhat special in some ways. What we can compare to, of course, are serosurvey results. We have data for cases and deaths currently across the whole period. And that's really what we tie our calculation, what we benchmark our calculation to. And we've used this, for example, to make projections for the state of Andhra Pradesh. So we have, in collaboration with the Epidemiological Committee of Andhra Pradesh, we have been looking at, so the pictures that you can see there are the first wave and then the second wave of cases, and then the number of cases coming down. This is up to the point at which the Omicron wave took off, and I will describe that a little later. So this is the period between June and September, where we made weekly projections across this period, looking at the number of deaths, looking at the number of cases, and you can see what our projections do. The band that you can see there are the band of our projections, and the dots that you can see are, of course, the data, the real data from Andhra Pradesh. We can use these models. In fact, they were used to estimate the number of hospitalizations, the number of cases requiring critical care, and also for drug procurement at that particular point. So that's where models are really useful, because they enable you to have some idea of what you can do with what you can do to plan for the future. We've also been looking at models for Omicron, and I will tell you about models for vaccination that we have been using in this context, because they enter, by the time the Omicron wave took off, a substantial number of Indians had already been vaccinated. Therefore, you need more complicated models that describe vaccination as well. These models, as you can see, are much, much more complicated. There are many, many different compartments. There's a compartment that represents the unvaccinated, a compartment that represents the single dose vaccinated, and a compartment that represents a double dose vaccinated. When we talk about Omicron, we do have data from South Africa to compare to, and much of our data, our calculations for India, are benchmarked to the case of South Africa, which is similar to India in many ways. In India, specifically, we have to account for the effects of prior infections, across the alpha, original wave, across the delta wave, etc. And all of these go into describing the nature of these models and the projection that we can make from these models. We've used these to answer some very specific questions. One question was, why didn't cases take off in children once schools were reopened in Andhra in early August? That was one question. The second question was, what was the impact of the Omicron variant given the background levels of seroprevalence, the background levels of seropositivity in the population? What we find that since we're now able to change many things, we can alter the seropositivity, we can look at completely counterfactual scenarios where you have 20, 40, and 80% seroprevalence. That's in these pictures here, as well as the number that we have, which is 64% by early August of 2021. And we can look and see, and the answer here is that already there were enough people infected in Andhra Pradesh by the time the Omicron wave took off and the time the schools were reopened, that we really didn't see much impact on schools, on increase in children's cases. Had the seropositivity been lower, as it was in some of the districts of Andhra Pradesh, we would have expected to see a larger increase in the number of cases in children. We can also look at the differential impact on both adults and children. When you open schools, because children have not been vaccinated, they're the people who are likely to be infected, and they will take these infections back home. On the other hand, adults already had, the 18 plus population in Andhra Pradesh already had a fairly high level of vaccination by that time. So we can ask, what is the impact of this on adults? What is the impact of this on children? And this is exactly the sort of questions that we've been looking at in terms of Omicron and in terms of the previous wave of COVID-19 in that state. We can do this for any state in the country. And we have, in fact, done these arguments for a number of states. I want to now tell you about, in the last 10 minutes that I have, about more complex models and their relation to policy. The first thing that you can do is to put the heterogeneity back in. And the way this is done is to study network and agent-based models. And what we've been doing is we have been looking at testing strategies, at school reopening, and a model that I will call BharatSim. BharatSim is something that we have pioneered at Ashoka University with our collaborators. And I want to tell you a little bit about the power of that method, the power of that technique in being able to understand the spread of an infectious disease. One question that we were asked fairly early on is that India uses two COVID-19 tests. One is a high sensitivity test, an RT-PCR test, and the other is a low to intermediate sensitivity rapid antigen test. Given this, the question that you could ask are, how much should you be testing your population if you want to control the disease? What is the optimal mix of RT-PCR to RAT? What does that mix depend upon? And as the cost difference between these tests varies, how should the mix be changed? Because these are both economic questions as well as questions about disease control. The way we model this is through networks. We have a model that describes homes, workplaces, hospitals. We put in the structures of homes anywhere between 2 and 8 family members per home, the number of family members and that the ages of those family members. You have people who go to work, to school, etc. And we describe the transition between these places. Once they're ill, they move to hospital. And the picture that you can see to the bottom right is the picture that describes how disease spreads across this network and the increase in cases as it goes up and goes down. And now we can ask exactly these questions from here. If we now imposed a certain testing regime on those who were infected in this particular network, how would things change? So you can vary the testing rate. So these are all graphs in which you see the fraction of rapid antigens going from 1 to 0 on this axis. You can see the rapid antigen test sensitivity because there are tests of different sensitivity. Currently, anything above 50% is usually acceptable, but we have had sensitivities all the way from about 70% to about 85% in this case. And finally, our metric is the total number of people infected. And you can look at this at different daily testing rates all the way from 0.1% to 0.9%. You can change the varying quarantine procedures. You can quarantine when you declare that someone is positive. You can quarantine when you sample. Just ask them the moment they come in to be tested. You can say, please quarantine yourself until you get your results back. You can look at the daily testing rates. So you fraction the rate as a function of both RAT sensitivity and the fraction of RAT. And you can ask what is the impact of that. And finally, you can look at other NPIs, the non-pharmaceutical interventions. For example, various combinations of lockdowns, etc., can be studied within this model. What are the results? So here the paper appeared in PLOS Computational Biology a few months ago and was highlighted in a bunch of places as a general approach to understanding testing in low and middle income countries. You should test somewhere between 0.2% and 0.5% daily was our recommendation. India was testing at a little less than 0.1% at the time that the paper was written. Actually, it turns out that if you ask what is the optimal mix of RT-PCR to RAT, it turns out that even all RAT regimes are okay if you test enough. This depends upon where you are on the epidemic curve, how sensitive your test is, and the amount of testing that you can actually do. The second question that we were asked is what happens when schools will reopen? And schools largely reopened across the Indian states on September 1st, 2021, and they were subsequently closed during the Omicron wave. The questions here was, will cases rise? What happens to children and family members? Should the non-pharmaceutical interventions continue? And should states explore different strategies? Over here, this is work that we did for the World Health Organization, the Strategic Advisory Group on Emergencies. And here we took the same sorts of network models, but augmented them with schools. So you had homes, workplaces, schools, and hospitals. You described the movement of people, and we looked at communities in which you had a school community of about 20,000 people sending children to schools with a proper distribution of ages of members of the community. We can now ask, at this given vaccination level of 0.2% vaccination per day, what would the difference between adults and low risk children be? What if you had vaccination, if you didn't have vaccination? How does vaccination help to blunt the effects of the disease? So our conclusions were, first of all, will cases rise when schools reopen? We said yes, mainly in children, but we expect very minimal serious illness. It was better to look for symptoms than to treat accordingly. We found that family members were largely protected by prior infection and vaccination, so we expected a smaller rise there. But we also suggested that you prioritize family members for vaccination. We said that NPI should continue non-pharmaceutical interventions. These are the interventions such as lockdowns, mask wearing, etc. And we said these will all help to cushion the impact and describe different strategies for relaxation. We said Indian states should all explore different strategies that depended upon their level of seropositivity, how many infections they had earlier, and for this you needed more granular information. We looked at other countries apart from India, and we said the experience of each country was different. There were many confounders, so you could not really take information derived from one country to apply it to this particular context. We also wrote about this in public venues to describe what was the nature of our calculations and the impact that it had on public health policy. Finally, let me tell you about Bharatsam before I finish up. Bharatsam is a computational method that really uses the current state-of-the-art computational techniques and methodologies to try and simulate how disease proceeds in a population. So what you need for this is a very, very large-scale synthetic population. So we describe populations pretty much at the level of every state of the country. And we have a simulation framework that describes how people move back and forth between homes, workplaces, population densities, etc. And we also have a visualization tool that describes, so you can see the results of this on the left-hand side, where we look at how disease spreads through Pune city. The synthetic population is drawn from various health surveys, census, etc., etc., etc. And once you have this, you can then ask, within this population that you study, how does disease spread? Can you correlate that to what you understand? How do variants make a difference? How do people make economic decisions on all of this? So look at the picture here. This is the picture that on the top left. This is for Pune. This is the number in millions. So we had a population of about 3 million people and asked how does disease spread in that population of 3 million people, where the population is described in as realistic a manner as possible. We can also take this and look at the effects of reinfection. What happens if you have 100% reinfection or a much smaller chance of reinfection? And there, the fact that many people have already been infected earlier makes a difference to the nature of the curve. And we can do all of this in fair amounts of detail. We can look at it at the level of Bombay. We can sort of ask how disease spreads within Bombay. You can see how the scarf that you can see darkens as different regions or different zones within Bombay have more and more cases. We can model totally now up to 50 million agents. We can look at a variety of different model communities. We have applied the same analysis that we did in the network model to these more refined agent-based models. And the plan is in the future to also study vector-borne diseases, effects of temperature, of climate change, etc., in this way. Last, let me come to the Omicron wave in India. We worked on the Omicron wave and pretty much showed that we expected the peak of the Omicron wave in India, in the largest cities, to come between about the 20th of January and about the 8th or the 8th of February, roughly, so the 5th of February, roughly speaking. We suggested when the wave in Karnataka, in Bombay, etc. would come. And this was pretty much accurate in terms of, as it turned out, we predicted the number of cases. We said that, and as the number of cases that we would see in the unvaccinated, the vaccinated, and the vaccinated with 1 dose and 2 dose populations. This was part of a suite of programs that many people contributed to, which was highlighted in a web page that was set up by Siva Atreya and Rajesh Sundaresan of Bangalore. And this provided a repository for different projections. And most projections by then were in rough agreement with each other, but ours was the most detailed because it could actually tell the difference between people who had been vaccinated with 1 dose or vaccinated with 2 doses. To conclude, let me talk about the fact that when we think about modeling, we really need to think about a variety of models that span many different types. I described a bunch of different models to you just now. I told you about compartmental models, the incising model. I told you about the network model that we use to describe testing as well as school reopening. And I told you about the far more complicated agent-based models that are the state-of-the-art models for thinking about disease spread. The agent-based models are very granular, they're very powerful, they can describe how people change their behavior as more information comes in. There are also pure statistical models that are machine learning models, but it's a little harder to use these to understand and to be able to make the sort of interventions, to ask in the future what would happen if I imposed a lockdown, if I came up with a better vaccine, if I improved my vaccine rollout. These are questions that you can tackle much better with models of the sort that I described, rather than these other somewhat far more theoretical computational science types of models, such as machine learning models. The usefulness of models, of all models, is really to make short-term projections. You should not trust models that project over a longer time period. You should ask, what can I expect over the next week to 10 days? And then the uncertainties take over. So anything on any model prediction for a time that is larger than that is really a very uncertain projection. Models are useful insofar as they can help you detect policy. They can direct you in the right direction. They can ask you about what the combined effect of multiple interventions might be. That's where they're really useful. I used the word ensemble models a little earlier to suggest that no single model should be relied upon. The best way to think about modeling is for many people to work on many different models together and then to be able to combine that into an ensemble of models from which one can extract one single average projection with uncertainties and errors. Then once one begins to do this better, one can weight in models with different weights depending upon which models have performed better in the recent past versus which other models. This is a common technique that is applied, for example, to weather forecasting, where a weather forecast is usually obtained by taking an ensemble of different projections and putting them together. Of course, all of my work is done in collaboration with a remarkable set of people. The group that I worked most closely with are Sandeep Krishna, Philip Cherian, Brian Wall, Vaibhav Sen, and Farina Muzaffar, all people across multiple institutions in Chennai, Pune, Bombay, Bangalore, etc., etc. And of course, I have relied very much from talking to a bunch of senior colleagues of very high quality who have, who have shown me the right directions to think about, who have suggested problems that are important for modelers to be associated with, and have helped to strengthen the overall contribution of modeling to the description of disease of COVID-19 in India. So I don't want, so while all of the work that I've described to you so far have been related to COVID-19 and our own work on COVID-19 in the last 2 years, these models are now general. We have now been able to describe these models in some detail. So we can apply them to multiple situations, to multiple scenarios of infectious diseases, as well as non-transmissible diseases, again, which we're interested in, such as diabetes or cardiovascular disease or COPD. So the importance, modeling is one important component of being able to plan for the future, to be able to think about strategy. And that's really the point that I would like to emphasize, that the importance of modeling, the importance of modeling exercises is really in that it enables you to think about what policies might be most effective, what policies might be the most targeted in the future. And that's where I think the importance of these exercises comes from. With that, let me stop here. Let me thank you very much for your attention. And let me figure out how to stop presenting and I can come back here. Yes, there we are.
Okay, thank you, Dr. Gautam. Thank you, Dr. Gautam, for your interesting, brief, and crisp lecture on testing and modeling strategies for COVID-19. Thank you once again, sir. Hope you stay connected with us. Uh, Now we proceed to invited lecture of this session. We have invited lecture from Dr. Varsha Poddar. She is from ICMR NIV